Compressible flow, the introduction. In previous lesson, we learned about laminar and turbulent flow, and I think this is, you still remember about laminar and turbulent flow. We check the flow with a Reynolds number, and for representative flow in pipe, for example, flow in pipes, we check its Reynolds number. If the Reynolds number is less than 2000, so we categorize that flow is a laminar flow. If the Reynolds number is more than 4000, then we could say that flow inside that pipe is in turbulent. Then in last chapter, we learned about the ideal and real fluid. So the ideal fluid is we assume that that fluid has no resistance. So we learned about this in ideal flow or potential flow, where we calculate everything without include its resistance. And now after that, we learn about the real fluids. So real fluid is we calculate everything included its resistance. So in previous lesson, we learned about real fluid in chapter of boundary layer. So in this chapter, we consider flows of gases in which the density changes significantly between points on a streamline. Such flows are called compressible flows. So it's mean that in previous lesson we learned about fluid, especially liquid. So we learned about water flow in pipe and so on and so forth. And our assumption is that fluid is incompressible. So incompressible means the density of that fluid is not changed. But now in this lesson we learn about a fluid, especially gases, that could be compressed, and we call that as a compressible flow. So I hope in this chapter you realize that everything has its pair. If laminar, it has turbulent. If ideal, it has real fluid. If incompressible, it has compressible flow. So for incompressible, in previous lesson, we usually solve problem about low speed flow and the density is assumed. So the basic equation that we use in incompressible flow is we are using volume flow rate. So we have Q1 equal Q2. So the unit will become meter cube per second. And then we will use Bernoulli equation. So this is the Bernoulli equation. I think you still remember it. So as you see here, so we have terms of rho here, but the rho is constant. That we don't have any rho 1 or rho 2 because the density is constant. Now, in this chapter, we will learn about compressible flow. Usually, compressible flow is deal with gases in high speed because it is very, very difficult for us to make liquid move in high speed. So usually we will deal about gas in high speed, and as you know, gas can be compressed, so means that the density of gas might be changed from point 1 to point 2, from inlet to outlet, and so on and so forth. So the basic idea here is we cannot use volume flow rate. We will use mass flow rate, so which the unit is kilogram per second. And then please remember this, in compressible flow, so we cannot use Bernoulli equation. So if you solve compressible flow problems by using Bernoulli equation, it's totally incorrect. So what we use is the mass flow rate. So mean mass at inlet is equal to mass at outlet. Then we could rearrange the term of mass flow rate here by using this equation. Rho 1 A1 V1 equal to rho 2 A2 V2. So means the density here might be changed from a certain value to another value. And then again, I would like to say here that Bernoulli equation cannot be used in compressible flow. Okay, for example, what is the common example for compressible flow, compressible fluid? So the common one I would like to say here is our cooking gas. So we could say that it is compressed into liquid form in this tube and then released as a gas from our stove gasket. So it changed its phase from gas into liquid in the gas container, and then when the valve here open, so it will release as a gas back. So that gas is flammable, so we could use that for cooking. So here we compress the gas and it's changed its phase from gas to liquid. So another example is our tire, air in car tires. We pump air into the tire with a pressure valve with a certain pressure value. The pressure entered is higher than the atmospheric pressure, but the air phase is still gas. It does not turn into liquid. So I think everybody could drive, everybody know about tire and how to pump and air into tires. So this is might be the common level that we could see in our car. So means we have to put around 230 kilopascal for in our front tire for this car to make sure. So this means that we compress the air inside this tire, so the pressure inside this tire is higher compared to the atmospheric pressure. Before we go deeper in compressible flow, I would like to introduce to you a few equations that we already learned in thermodynamics, I think. So because we will use this equation extensively in this chapter. So first we will deal with gas, and for sure we will need to use the ideal gas law. So please make some revision about ideal gas law, which is P is equal to rho RT. P here is the pressure in absolute as an absolute pressure. Rho is the density of the fluid, and R is the specific gas constant, and T is the absolute temperature in Kelvin. So R for air, for example, is the universal gas constant divided by air molecular mass. So it is about 8,314 divided by 28.97, and then finally we could get the gas constant for air is 287 joule per kilogram Kelvin. Please remember this number because this number will not be given in the exam. So this is a basic parameter that you need to remember in compressible flow. So please take note that the molecular mass of air is a little bit special because air is consists of certain percentage of a few type of gases. It is not only oxygen alone or nitrogen alone, so it is a mixture of them. So we take the universal value of molecular mass for air is 28.97. So please remember this in your calculation. For example, if we need to calculate what is the specific gas constant for carbon dioxide, so what we need to do is we just divide the 8314 with 44 because 44 is the molecular mass for carbon dioxide, which is carbon is 12 and oxygen is 16 times 2 is 32. So the total is 44 and we get it is 189 joule per kilogram Kelvin. And then for specific constant gas here R can be determined as Cp minus Cv, which is Cp is the specific heat at constant pressure and Cv is the specific heat at constant volume. And the specific heat K, sometimes written as gamma, can be calculated by using this equation where Cp over Cv, and Cv can be calculated as 1 over K minus 1 R, and Cp is equal to K over K minus 1 R. So I just give you a few equations for calculating gas here, and please make a revision of thermodynamics by yourself. For example, if we want to calculate the value of specific ratio K for air, so it is around 1.4. So this is also a constant number that you need to remember to solve problem in final exam. And the value of K over K minus 1 is 2.5, and K over K minus 1 is equal to 3.5. And from the ideal gas law also, we could found that T2 over T1 is equal to P2 over P1 by the power of K minus 1 over K, and P, which is pressure, P2 over P1 is equal to rho 2 over rho 1 by the power of K, which is T is the temperature in Kelvin, P is the pressure, rho is the density, and K is the specific ratio. And then in our syllabus, we will always say about adiabatic process and isentropic flow. So in thermodynamics, an adiabatic process is one that occurs without transfer of heat or matter between a thermodynamic system and its surroundings. In an adiabatic process, energy is transferred to its surroundings only as work. The adiabatic process provides a rigorous conceptual basis for the theory used to expound the first law of thermodynamics, and as such, it is a key concept in thermodynamics. An isentropic flow is a flow that is both adiabatic and reversible, means there are no losses. That is, no heat is added to the flow and no energy transformations occur due to friction or dissipative effect.